Jai Hind to all. Myself Richa, Assistant Professor in Department of Electronics and Communication of Ajay Kumar Garg Engineering College. Today we will discuss about the topic waveguide. So waveguide is a hollow metallic tube of a rectangular or circular shape which is used to guide an electromagnetic signal. Whenever we want to transmit any information, we want a transmission media for traveling of the signal. So in the waveguide or microwave signals, we required a guided media. So waveguide is guided media which is used to transmit electromagnetic wave. In waveguide, the electric and magnetic fields are confined to the shape within the guide. So there is no loss of the power because of the radiation. However, there are some dielectric losses which is very negligible because of the wave striking at the inner wall of the guides, but these losses are very small. It is possible to propagate several modes of electromagnetic wave within a waveguide. These modes correspond to the solution of the Maxwell equation for a particular waveguide. Whenever any electromagnetic signals are traveling through the waveguide, they are a combination of electric and magnetic field. So we will solve this complete traveling of the wave through Maxwell equation. The first mode which is traveling through the waveguide is the dominant mode. So dominant mode is for a particular guide is the mode having lowest cutoff frequency, and in terms of the wavelength it is having the highest cutoff wavelength. So a waveguide will behave like a high pass filter. So any signal which is having a frequency higher than cutoff frequency will allow to propagate through your waveguide. So if we want to solve Maxwell equations for a waveguide, so we require three steps. First step is the desired wave equations are written in the form of some coordinate system. If we are dealing with the rectangular waveguide, so we will write it in the rectangular coordinates, right? And if our waveguide is in the form of cylindrical or circular, we will use the cylindrical coordinates. After that, we will apply boundary condition to our setup. So after applying the boundary condition, the resultant equations are coming, which is generally in the form of partial differential equations, right? So the solution of partial differential equation either in the form of time or frequency domain. So by using a proper method, we can find out different equations of Maxwell by using partial differential equation, solution of that equations. So see here, this is the rectangular waveguide. Whenever a plane wave coming into the rectangular waveguide, it will strike to the wall of the waveguide, and from here it will be reflected back to next wall, and from here again it will be reflected to next wall. It means the reflection of the signal is through total internal reflection. So whenever a plane wave is entering into the waveguide, it will be resolved into two components. One component which is normal to the direction of the propagation, it means this is the direction of the propagation, right? If I assume that direction of propagation is z, right? And next component which is parallel to the direction of propagation, that is lambda p. So now when the plane wave is entering into the waveguide, it will be resolved into two components, lambda n and lambda p. It means now the plane wave is not in the form of TEM wave. It will be converted into transverse electric wave or transverse magnetic wave. So from the last figure, we can calculate the value of lambda L by using Pythagoras theorem. Lambda n is equal to lambda upon cos theta and lambda p is equal to lambda upon sin theta. And lambda is the wavelength of the signal which is entering into the waveguide, and theta is the angle of incident. So there are basically two components of the wave. First component is lambda n, that is in the direction normal to the reflected plane, and second one is the lambda p, which is in the direction parallel to the plane. So plane wave in the waveguide now resolve into two components. First is called one standing wave, right? And standing wave component is responsible for movement of the waveform. So it is direction normal to the reflecting walls of the guide. Next is the traveling wave. It means through this component your wave will be travel from one end to another end, and this is one traveling component which is normal to the direct reflecting wall, right? So it means now your wave is converted into two type of waveform. One is the transverse electric mode and another one is a transverse magnetic mode. So transverse electric mode, it means in this you are magnetic field in the direction of propagation is 0, and transverse magnetic mode, it means here the electric field in the direction of propagation is 0. Generally in the rectangular waveguide, the modes are designated with TE-MN or TM-MN. This M and N subscripts are used. M is for your denote the number of half wave of electric or magnetic intensity in the direction of X, and N denote the electric and magnetic field electric and magnetic field intensity in the direction of Y. So now the second step, we will solve the equation, wave equation, using rectangular coordinates. So there are time domain and frequency domain solution for each of the wave equation. However, simplicity of the solution to the wave equation in 3 dimension plus a time varying variable, only sinusoidal steady state or the frequency domain solution will be used. So here in the figure we show the rectangular coordinate system. Here X direction, Y direction and Z direction. Z direction, here the signal is propagating into the Z direction. This is your rectangular coordinate, and here we have placed a one rectangular waveguide, right. So as we know, rectangular magnetic wave equation, the frequency domain is del square E is equal to gamma square E in terms of electric field. Del square H is equal to gamma square E in terms of your magnetic field. So where gamma is the propagation constant, which is equal to square root of j omega mu rho plus j omega epsilon, and it is equal to alpha plus j beta. Alpha is your attenuation constant and beta is the phase constant, right. Beta is used for phase constant. So rectangular component of E and H satisfy the complex scalar wave equation, and this equation is del square xi is equal to gamma square xi. So when we want to resolve this equation into the rectangular coordinate, it means now we will write this equation in terms of x, y, z direction in all the 3 coordinates. Del square xi upon del x square, del square xi upon del y square plus del square xi upon del z square is equal to gamma square plus xi. So this is your equation number 1, and equation number 1 is the linear and inhomogeneous partial differential equation in all the 3 dimensions. So this linear inhomogeneous partial equation can be solved by method of separation of variable. So by using method of separation of the variable, the solution is assumed to be xi is equal to xx, yy and zz. Here this xx is the pure function of x only, right, pure function of x only, and yy is a pure function of y only, and in similar way zz is a pure function of z only, right. So we can rewrite this as x, y and z. Now substitute the equation number 2 in equation number 1, and this after putting the value of 2 into 1, then complete resultant will be divided with x, y, z. Then finally we get 1 upon x del square x upon dx square plus 1 upon y del square y upon dy square plus 1 by z upon del square z upon dz square is equal to gamma square. Again if we see that this is a pure function of x only, y and z, right. So it means this is a pure function of x only x, y and z, and this first term is dependent only on x. It means it is independent of y and z. So if any term which is independent to other factors, we can consider it as a constant also. So since the sum of 3 terms on the left hand side is a constant and each term is independent variable, so it follows that each term must be equal to constant. So we can consider that for x, y and z coordinate, we can write equation as follows: del square x upon del x square is equal to minus kx square x, one of the constant in x direction. Del square y upon dy square is equal to minus ky square y. D square z upon dz square is equal to minus kz square z, where minus kx square, minus ky square, minus kz square are the constant in the direction of x, y and z. Now using these three equations, your equation number 3 can be written as minus kx square minus ky square minus kz square is equal to gamma square. So from the last three equations, the general solution of each differential equation can be written as x is equal to a sin kx x plus b cos kx x. So this is the solution of first equation, or solution of your equation del square x upon del x square is equal to minus of, see this equation, minus kx square x. So solution of this equation is a sin kx x plus b cos kx x. And the second equation, del square y, d square y upon dy square is equal to minus ky square y. So the solution of this equation will be y is equal to c sin ky x plus d cos ky x. D square z upon dz square is equal to minus kz square z. Solution of this equation is z is equal to e sin kx kzx plus f cos kzx. Here a, b, c, d, e and f all are the constant. So the solution which we have assumed was xi is equal to x, y and z, and from these three equations we get the solution of x, y and z. So the complete solution of the wave equation is xi is equal to a sin kxx plus b cos kxx into c sin kyx plus d cos kyx, e sin kzx plus f cos kzx. So this is the final solution of your wave equation. Now the propagation of wave in the guide is conventionally assumed in the positive z direction, right? So the propagation constant gamma g in the guide differ from the eccentric propagation constant of gamma of the dielectric. So we can write propagation constant of guide is equal to gamma square is your propagation constant plus kx square plus ky square. So combiningly kx and ky can be written as kc square. I can write kc square is equal to kx square plus ky square, and it is called wave number, right? So kc is equal to under root of kx square plus ky square, and it is usually called the cutoff wave number. For a lossless dielectric, gamma square, it means the propagation constant is equal to minus omega square mu epsilon. If your gamma square is equal to minus omega square mu epsilon, so we can write guided your propagation constant is equal to plus minus square root of omega square mu epsilon minus kc square. So here three conditions will come for this. First is when both are equal. When your propagation constant is greater than cutoff wave number. When your propagation constant is less than cutoff wave number, right? Then the first case, in the first case, what is the condition? We are taking the condition that your propagation constant is equal to cutoff wave number. So this is the critical condition. Actually, this is the point where after that wave start propagating. So when we put these two are equal, so what will happen? Your guided your gamma g will equal to 0, or we can say guided propagation constant will be 0. If your propagation constant is 0, it means wave will not propagate, all the wave will be attenuated, right? So this is the critical condition for cutoff propagation, and the cutoff frequency is 1 upon 2 pi under root of mu epsilon square root kx square plus ky square, because the first factor is 0 here. So cutoff frequency will be calculated from this expression. Now case 2, when your propagation constant is greater than cutoff wave number. So what will happen? It means you will get a value which is equal to plus minus j beta j. It means here we are getting the imaginary value. So if you remember that propagation constant is equal to alpha plus j beta, it means here we are getting only this part. It means your wave will be propagated because attenuation factor is 0 here, and cutoff it can again written as plus minus j omega under root mu epsilon under root 1 minus fc upon f square. This means that the operating frequency must be above the cutoff frequency in order for a wave to propagate inside a waveguide. Now the case number 3, when your wave will be attenuated if propagation constant is less than cutoff wave number. It means if this factor is less, we are getting only attenuation factor. It means we are getting lambda z, and this propagation constant is 0 here. It means wave will not propagating. All the wave which is entering into the wave side will be attenuated 100%, and is equal to plus minus omega mu epsilon under root fc upon f square minus 1. So this means that if the operating frequency is below the cutoff frequency, the wave will decay exponentially with respect to a factor of alpha gz. Alpha g is basically attenuation factor with inside the waveguide, and z is used because your wave is propagating into the z direction, and there will be no wave propagating because the propagation constant is a real quantity, because all the wave which is entering into the wave side will be 100% attenuated. So therefore the solution of the wave equation in rectangular coordinate is xi is equal to a sin kxx plus b cos kxx into c sin kyx plus d cos kyx e की power minus j beta z. So this is the final equation, wave equation for rectangular waveguide. Now we will discuss about propagation of waves in rectangular waveguide. It means how the microwave signals will traveling through rectangular waveguide. So we are considering a waveguide which is placed along rectangular coordinates, and its breadth is along x-axis and width is along y-axis. So this is your breadth A and B, right? And wave is traveling into z direction. So this is your direction of propagation. And this wave guide is filled within air as dielectric. It means here the dielectric is used as a air. Now how microwave signals are behaving in this waveguide? So as we know, the wave equation for TE wave del square Hz is equal to minus omega mu epsilon Hz, and the condition is that for TE wave electric field in the direction of propagation is 0. Second equation, or we can say TM waveform, del square Ez is equal to minus omega mu epsilon Ez, and for TM magnetic field in the direction of propagation is 0. So first I will take TM wave. So if I am taking the TM waves, so expand this del square Ez into rectangular coordinates. So I can write del square Ez upon del x square plus del square Ez upon del y plus del square Ez upon del z square is equal to minus omega mu epsilon Ez. Since this wave is propagating into z direction, so I can assume one operator, that means del square upon del z square is equal to gamma square. Gamma is basically here propagation constant. So wave is traveling into z direction, so I am taking this as a operator. Now substitute this operator in this equation number 5. So it can be rewrite del square Ez upon del x, del square Ez upon del y square. In place of this I will write gamma. Gamma square Ez is equal to minus omega square mu epsilon Ez. So now this equation number 6 can be rewrite del square Ez upon del x square plus del square Ez upon del y square, h square Ez is equal to 0. So how it means this can be written as del square Ez upon del x square plus del square Ez upon del y square plus, here is the gamma square plus omega square mu epsilon, and this is complete Ez is equal to 0. So this factor we have used at one constant, that is h square. So it is written as h square. Similarly, for your TM mode, TE wave. So del in place of Ez, here it is Hz. Del square Hz upon del x square plus del square Hz upon del y square plus h square Hz is equal to 0. This is your TE wave. Again, what is this h? H is equal to gamma square plus omega square mu epsilon. So equation number, last two equations are the partial differential equation. So by solving the partial differential equation, we can have a solution of Ez and Hz. But we want all the component in all the three directions. It means electric and magnetic field in all direction, which are Ex, Ey, Ez, Hx, Hy and Hz. We require all the 6 component, right? So how these 6 component can we find out? It means from last two equation we can have a value of Ez and Hz. It means we require equation in all these equation in form of either Ez or Hz. So that after putting the value of Hz and Ez, we can find out Ex and Ey. So it is possible by using Maxwell equation, and by using Maxwell equation we can find out the various component along x and y direction. So Ex is written as minus gamma upon h square del Ez upon del x minus j omega mu upon h square del Hz upon del y. In the similar way, this is Ex, Ey, Hx and Hy. See, all these 4 equations are in terms of either Ez or Hz. So if we are having a value of Ez, we can find out all remaining 4 components. If I am having a value of Hz, I can find out all remaining 4 components. So first we will discuss about the TM mode. For TM mode, we have to apply some boundary conditions. So see here, what is that? Condition of TM mode is magnetic field along the direction of Z is 0, or magnetic field in the direction of propagation is 0, but there is the possibility of electric field. It means electric field in the direction of propagation is not 0. So we will find out what is the electric field in x and y direction also, and what is the electric field at the boundary of your waveguide. So see here, Ez is 0 at y is equal to 0 for all value of x ranging from 0 to a. This is first boundary. Second boundary, Ez is 0 at x is equal to 0 and y varies from 0 to b. This is your first boundary and second boundary. Third boundary, Ez is 0 at y is equal to b. Here y is equal to b and x varies from 0 to a. This is your third boundary. Fourth boundary, Ez is 0 at x is equal to a. This is your x is equal to a and y varies from 0 to b. So all these 4 boundary conditions we will use to find out TM waves. So the condition is same for TM mode. Hz is 0 but Ez is not equal to 0. So this is the general solution for TM wave traveling through waveguide. This solution we have find from the wave equations, solution of the wave equation from the previous slides. But change is that at the place of minus j beta z, I have written minus gamma, because here we are using gamma as a propagation constant and z is used because the wave is propagating into the z direction itself. So solution is that Ez is equal to a1 cos bxx plus a2 sin bxx into a3 cos ayy plus a4 sin ayy e की power minus gamma z. So first we will put first boundary condition in this equation, right? So what is the first boundary condition? See here. So first boundary condition is that Ez is 0 at y is equal to 0. So y is equal to 0, it means this will be 0 and this will be 0. Cos 0 will be 1 and sin 0 will be 0. So your equation will be reduced to a1 cos bxx plus a2 sin bxx into a3, and this is equal to 0. Okay. So if product of two things are 0, it means any one of these two components are 0. So we assume that this is your, after putting the first boundary condition, right? So I will assume that a3 will be 0. So this factor will be 0. So your main equation will be reduces to a1 cos bxx, a2 sin bxx, and this will be 0. It means a4 sin ayy e की power minus gamma z. Now in this equation I will put boundary condition number 2. Okay, so what is boundary condition 2? It says that Ez is 0 at x is equal to 0. Okay, so in this cos, this will be 0 and this will be 0. So cos 0 will be 1 and sin 0 will be 0. So it reduces to a1 into a4 sin ayy. So again I will assume one constant that will be equal to 0. So waveform will be reduced to a1. It means a1. Here I will write what is the, after applying the boundary condition 2, it comes out to be a1 plus this is 0 and a4 sin of ayy e की power minus gamma z, right? So either this factor will be 0 or this factor will be 0. We assume that a1 is equal to 0. So this equation will be reduces to a2 sin bxx, a4 sin ayy e की power minus gamma z. So now we will put equation number boundary condition 3 here, and it comes out to be sin ayy because at place in this condition y is equal to b here. So sin of ay b is equal to 0. So sin will be 0 at n pi. So ay can be written as n pi by b. Substitute fourth boundary condition in this equation, right? Fourth boundary condition we are getting, this will be the condition. So here x is equal to a. Sin of bx a is equal to 0. So here bx comes out to be m pi by a. So complete solution of this equation, I can write a2 a4 sin of bx x sin of a by y. So a2 a4 I will write e naught, sin of bx, in place of bx I will write m pi by ax sin of n pi by b y e की power minus gamma z. So this is the complete solution of your TM mode. So how another all remaining components can be found? So this is your final equation, e naught sin m pi by ax sin n pi by by e की power minus gamma z, and hz is 0 here. So from the equation number 7, 8, 9, 10, we are using ex. So minus gamma upon m square m pi by a e naught cos m pi by ax sin n pi by b e की power minus gamma z. So from equation number 7, 8, 9 and 10, we can find out the value of ex, ey, hx and hy, right? So now we will find out what type of modes are supported by the waveguide. If I am assuming TM 0, 0, it means m is 0 and n is 0, both are 0. So see here, if I put m is 0, n is 0, and here m is multiplied. So complete will be Ex will be 0 here. In the next case, this is multiplied with 0, so Ey is 0. Here it is multiplied by n, 0, and here it is multiplied by m, 0. So in this way we can find out which mode is supported by this. In the similar way, m0, n0, all the components are 0. So if I am putting m, see here, if I take the 0n, m is 0, see. So here multiply by 0, here sin 0 will be 0, it means complete term is 0, multiply sin 0 will be 0, and here multiply with the 0. So if I am putting the value of m is equal to 1 and n is equal to 1, then only we are getting Ex, Ey, Hx and Hy. So that's why we can say that the propagating mode in Tm1 is Tmmn, where m is greater than equal to 1 and n is also greater than equal to 1. So this is the mode, E field and the H field. See here Tm0, it means 2 cycle rotation, and this is Tm11, it means 1 half cycle variation x direction, 1 half cycle variation in the y direction, 1 half cycle this, half and half, like this, 2 1, 1 2, 3 1, right. So in this way we can find out the electric field and magnetic field in Tm modes. After that I will discuss about the TE mode. So condition of TE mode is that Ez is 0, it means electric field in the direction of propagation is 0, but magnetic field is not 0. Again I will write 4 boundary conditions. So first boundary condition state that Ex is 0 at y is equal to 0, x varies from 0 to a. This is your first boundary condition. Okay. Because here magnetic field is not 0, but electric field is 0. Again Ey is 0 at x is equal to 0 and it varies from 0 to b. Ex 0, Ey 0. Third boundary condition, Ex is 0 at y is equal to b and x varies from 0 to a. Third boundary. Fourth boundary, Ey is 0 at x is equal to a and y varies from 0 to b. This is fourth boundary condition, right? It means at the boundary electric field is 0 in case of TE mode. In case of TM mode, electric field in the direction of propagation is 0 only. And we can say electric field in the direction of propagation at the boundary is 0. And here electric field along x and y at the boundary is 0. So your general solution for TE wave, the difference is that here we are calculating in terms of Hz and solution is same, A1 cos kxx plus A2 kx. I can write it here bx and a bx, right, ay and ay here, right. So from it means this is the main equation. So from equation number 7 and 8 I can find out the value of Ex and Ey in terms of Hz. So this is your Ex and this is your Ey. Okay. So substitute first boundary condition. If I am substituting the first boundary condition, so your main equation will be reduces to A1 cos bxx plus A2 sin bxx, A3 cos ay, y e की power minus gamma z. Because the first boundary condition states that Ex is 0 at y is equal to 0. Y is equal to 0, it means cos 0 is 1, sin 0 will be 0. So A3, and I will consider this your, by solving this is your after applying solution of this equation after applying first boundary. Now I will substitute second boundary in this equation and equation will reduce to A1 cos bx plus A3 ay y e की power minus gamma z. Substitute third boundary condition in this equation, it means sin ay is equal to 0, ay is equal to n by b. In the equation number 16 itself, put the fourth boundary condition and we are getting bx is equal to m pi by a. So complete solution is Hz is equal to your A2 A4, which is written as H naught. Cos of Bx means m pi by Ax, cos of n pi by By e to power minus gamma z. So these are the propagating and non-propagating mode of TE mode. This is the final solution. H naught cos of m pi by Ax, cos of n pi by By e to power minus gamma z Ez. So what is the difference between TE and TM mode? In the TE mode, this term is cos and cos, and in terms of TM mode, these two terms are sine and sine, and here is the E naught, right? So by using equation number 7, 8, 9 and 10. So this is Ex, Ey, Hx and Hy. Non-propagating mode is only 0, 0. At 0, 0, all the field components are 0. All field components are 0, right? And all remaining modes will be travel. It means TM01, M0, Mn all will be propagating through TE modes. So these are the some formula which we are using to solve the waveguide. So h square, as we know, gamma square plus k square, it can be written as kx square plus ky square. Gamma is equal to kx square plus ky square minus k square. When wave is completely attenuated, so it is written as the condition when your omega square mu epsilon is less than m pi a square plus n pi by b square. When your wave will be propagating, it means gamma is equal to j beta. This is your propagation constant. It means omega square mu epsilon is greater than m pi by a square plus n pi by b square. So it can written as omega is greater than equal to 1 upon under root mu epsilon of this, or in terms of frequency, it can written as frequency is greater than equal to 1 upon 2 pi this. It means the signal which is greater than this frequency will travel through the waveguide. Cutoff frequency when your gamma is equal to 0, it means when both are equal. This is your cutoff frequency. Waveguide will behave like a high pass filter. So this is your cutoff frequency formula. 1 upon 2 pi under root mu epsilon m pi by a square plus n pi by b square ka square root. In the simplest form, it can also written in this way. Phase constant beta is defined as under root k square minus m pi by a square minus n pi by b square, or mu under root mu epsilon 1 minus fc upon f ka square. In centering impedance can be found by ex by hy or minus of ey upon hx. So finally it comes out to be eta naught under root 1 minus fc upon f square. This is in case of TM. In case of TE, again ex by ey or minus of ey by hx, it comes out to be eta upon under root 1 minus fc upon f square. Phase velocity omega upon beta, so it comes out to be b upon under root 1 minus fc upon f square. Group velocity is given as 1 upon del beta upon del omega, so it comes out to be v under root 1 minus fc by f square. So if I will multiply bp into bg, so it comes out to be v square. Here v is the speed of light. So first two modes are very important here. First the degenerative modes. So whenever two or more modes have the same cutoff frequency, two modes if they are having the same cutoff frequency, they are said to be degenerative modes, right? In a rectangular waveguide, the corresponding TEMN and TMMN modes are always degenerated. In a square guide, TM, TEMN, TENM, TMMN and TMNM modes form a degeneracy. Dominant mode, the mode with the lowest cutoff frequency in a particular guide is called as a dominant mode. The dominant mode in the rectangular waveguide with A is greater than B is always TE10 mode. Each mode has a specific mode pattern. So today we have discussed about the waveguide and how wave equation, electromagnetic wave is traveling through the waveguide and what is the solution of wave equations. Jai Hind to all.